Yeah, so today I wanted to give somehow an introduction to what we're going to do this term. So this talk is called Introduction to Homotopical Algebra. And I will start from a very general idea of what we're trying to do here. So assume that we have a category C. And also assume that there is a distinguished class of morphisms in C, denoted by W. So these morphisms will be called weak equivalences. And we want to do some kind of homotopy theory with respect to W. So that's the general idea. And of course, there are many examples. Let me give a few. So there is category top of topological spaces. With W given by continuous maps such that so continuous maps, i.e. morphisms in category top, such that when we apply the homotopy groups functor, we obtain an isomorphism. So that's one way to define a class of weak equivalences. Another way, we can say that we want such maps that F is a homotopy equivalence. So obviously, those two are not the same thing, and depending on which class of weak equivalences we choose, we obtain different homotopy categories of topological spaces. So this first one is Serre homotopy category. So gives us Serre homotopy category. And this one gives us Horevich homotopy category. So next example is also, I think, quite familiar. Let A be the abelian category of R modules for some ring R, not necessarily commutative. And consider the category of chain complexes on, well, for simplicity, non-negatively graded chain complexes in this category. Then, well, really, for this example, it doesn't matter that they're non-negatively graded. We can just state that weak equivalences should be quasi-isomorphisms. And actually, the same thing applies if we take A to be an arbitrary abelian category. Okay. So similarly, one may consider commutative differential graded algebras over some field or ring, and weak equivalences once again should be quasi-isomorphisms. Okay, finally, simplicial sets with weak equivalences given by, if you will, weak equivalences induced from topological spaces. So we take the geometric realization functor, and we take pre-image of weak equivalences in topological spaces. I.e., those are precisely the maps in simplicial maps, such that when we apply homotopic groups function to the geometric realization of this simplicial map, we obtain an isomorphism. Okay, so those are some examples where it is natural to consider these, so to speak, relative categories, where we have a category and subcategory of weak equivalences. However, usually it is not sufficient just have a subcategory to do some meaningful homotopy. So that is why the notion of model category comes into play. So let me expand on it. So the classical approach of Quillen introduces the notion of model category, which is a category with slightly more information than just a class of weak equivalences. Namely, there's a category with three distinguished classes of morphisms. So these three distinguished classes of morphisms are, as already mentioned, weak equivalences, fibrations, and cofibrations. It is customary also to define two additional classes, which are just given by intersecting the respective class with weak equivalences. So we obtain trivial or acyclic fibrations. and we obtain trivial or acyclic or acyclic. Those are just names for the same thing. So trivial or acyclic cofibrations. These three classes should satisfy some additional properties. So let me give a definition. So we have 5 axioms of model categories, of a model category. So let M be a category. We say that it is a model category if it satisfies 5 axioms. So the first axiom is that M is bicomplete. So let D be an arbitrary small category. Then we require that the diagonal functor has right and left adjoints. So this is a functor of constant diagram, and we should have all limits and colimits. In other words, M is bicomplete. Another axiom is the so-called property 6 for 2. This is not the usual definition. So this is not a usual axiom for model categories. Usually it is required to have a property 3 for 2. And the property 6 for 2 is a slight strengthening of this property 3 for 2. But the idea is as follows. So consider 3 morphisms in our category such that 2 compositions, SR and TS, belong to the class of weak equivalences. Then the remaining 4 morphisms, namely RST and the triple composition TSR, all belong to weak equivalences. So that's another axiom. The third axiom states that the classes of fibrations and cofibrations should be closed under taking retracts. So what does it mean to take a retract of a map? Well, basically it means that we have the following commutative diagram. So, or let me state what I'm drawing here. So map F is a retract of the map G in M if we have the following commutative diagram. So one can say that we can split F from G. Yeah. Well, of course, there is a notion of retract subobject for any object in a category, and here we just say that F is a retract of G in category of morphisms of M, where objects are morphisms in M and arrows are just commutative squares in M. Okay, so that's the third axiom. The fourth axiom is about lifting properties. So we have the following lifting properties. So cofibrations have the left lifting property with respect to trivial fibrations. What does it mean? It means that if we have an arbitrary cofibration, which is, by the way, denoted like this, and here we have an arbitrary trivial fibration, which will be denoted like that. So two-headed arrow means fibration, and this equivalent sign means that it is trivial. Then there should be, and so we have this commutative square, and there should be the dotted arrow, which makes two triangles commute. And also we have a dual lifting property. In particular, fibrations have the right lifting property with respect to trivial cofibrations. I don't think that another diagram is needed. I think it's pretty straightforward. What does it mean? Okay, so finally, the most controversial axiom of model category, so to speak, is the factorization axiom. So let F be an arbitrary map in model category, arbitrary morphism. Then F admits a functorial factorization of two forms. So F could be represented as a composition Qi, where Q is a trivial fibration and I is just some cofibration. And also F could be represented as Pj, where E is a fibration and J is a trivial cofibration. Yeah, sure. I think we can talk about it, but maybe not today, because today I just wanted to talk about some very general picture. But yeah, thank you for this comment. Okay. Now I want to just sketch how a model structure can be constructed on each of the examples above, where we had this kind of relative category with equivalences. So let me sketch model structure on topological spaces. It is customary to call this particular model structure Quillen model structure, because he proved a certain theorem about equivalence of this model structure and certain model structure on spatial sets. So let F be a morphism model category. Morphism in topological spaces, in category of topological spaces. And we say that F is a weak equivalence. If it is an isomorphism on homotopy groups. So F is a fibration if it is CR fibration, meaning that it satisfies the lifting property with respect to inclusions of the following form. And finally, F is a cofibration if it is a retract of a relative cell complex. So what is a relative cell complex? Well, let me explain what is an attachment of a cell. We just consider a push out of the following form. And then a relative cell complex is any topological space that can be obtained as a possibly transfinite composition of single cell attachments. Okay, so okay, so that's of course now I will not prove that this definition indeed gives a model structure on topological spaces, mainly because to do so I will need to explain the small objects argument, which I will do in some next talk. But basically that is one way to define model structure on topological spaces. Okay, so now let me define two model structures on chain complexes. Okay, so for simplicity, let A be as before category of R modules, and consider a category of non-negatively graded chain complexes. Then weak equivalences should be quasi-isomorphisms. Vibrations should be epimorphisms. In degree greater than 0, and cofibrations should be monomorphisms with projective co-kernel. Dually, one may define an injective model structure so that this is a projective model structure on chain complexes. One may also define an injective model structure. But now on co-chain complexes, and this is done very similarly, so weak equivalences are the same. Vibrations are epimorphisms with projective kernel, with injective kernel. And cofibrations are just monomorphisms in positive degrees. Okay, so another similar example is the model structure on differential graded algebras. I think that I will restrict to the case of commutative differential graded algebras. So K be a field of characteristic 0. Then we have a projective model structure on connective commutative differential graded algebras over this field. So connective just means non-negatively graded. So weak equivalences are, once again, quasi-isomorphisms. Vibrations are epimorphisms in all dimensions. And cofibrations are defined by the lifting property. So this is just a class of all maps with left lifting property with respect to trivial vibrations. Okay. So this is obviously another example, which is quite important in rational homotopic theory. Maybe sometime in the future we will talk about this. Okay, so I want to finish this list of model structures with Wheeler model structure on special sets. Here, everything is pretty simple. So weak equivalences are just ones that induce isomorphism in homotopic groups. Of geometric realization. So fibrations are confibrations. We'll definitely talk about this stuff later. And cofibrations are just monomorphisms of simplicial sets. Okay, so now I want to talk about the reason why model categories are so useful. So one of the primary reasons is that so one of the main features of model categories is an explicit construction for the localization in subcategory of weak equivalences. So generally speaking, if we just have some subcategory and we want to localize in it, we may obtain something very strange in the sense that we may have some set theoretical difficulties arising from the fact that morphisms in the localization are just zigzags of morphisms from the initial category with some arrows from this subcategory. And so this new localized category may not be locally small for that reason. But for model categories, we actually have a pretty decent description of Hom sets, and they're really sets in this localization, which is, by the way, sometimes written as homotopic category of M. So this is just by definition the localization in the class of weak equivalences. So one useful observation is the following. So let me first define two classes of objects. So let X be an object of model category, then X is fibrant if the map from X to the terminal object is a fibration. And X is cofibrant if the map from the initial object to X is a cofibration. Now we have, well, this should be some kind of proposition. Which I will not prove today. So let M lower C be a subcategory spanned by cofibrant objects. And similarly, let MF be a subcategory spanned by fibrant objects, and denote by MCF their intersection. So a subcategory spanned by fibrant and cofibrant objects. Then we have the following commutative square, where each arrow is an equivalence of categories. So here, these functors between homotopic categories or localizations are induced just by inclusions of the respective subcategories into larger categories. Why this commutative square is useful? Well, the main reason is that this homotopic category of MCF can be computed rather explicitly. So we have for morphism, for a well, class of morphisms a priori between two objects, that is in fact just the quotient of regular morphisms in the initial model category modulus some equivalence relation. So let me define this equivalence relation. So let F and G be two morphisms in the model category. Then the cylinder of B is a canonical factorization of the Fulton map from B from a coproduct of two copies of B to B into a trivial fibration and cofibration. So this should be denoted by P times I. So since the factorization is canonical, we have a unique such object. Analogously, better yet dually, we have a path object of an object X. So path object of X is an object that comes from the factorization of the diagonal map. So we have a diagonal map from X to X times X, and we have canonical factorization. Here we take a trivial cofibration, and here we take just some fibration. And now we can define the notion of left and right homotopy between morphisms. So left homotopy from F to G is H from P times I to X that fits into the following diagram. Very similar to what we have for topological spaces. And analogously, we define the right homotopy is a map from B to the path object of X. So right homotopy from G is K from B to the path object of X. That fits to the following diagram. So we will denote left homotopy like this and right homotopy like this. And we say that two maps are just homotopic. If they are both right and left homotopic. So the main feature of fibrant and cofibrant objects is that if we have objects that are both fibrant and cofibrant, then on this set, notion of left and right homotopy coincide. And it is an equivalence relation. Which means that we can take a quotient of this set by this equivalence relation. And as it turns out, another important feature of fibrant and cofibrant objects is that a map from X to Y is a weak equivalence if is a homotopy equivalence that means that it has a homotopy inverse which goes in the opposite direction and whose composition with F is homotopic to the identity on Y in one direction and the identity on X in another direction. So you may think of it as a model theoretic analog of Whitehead's theorem about weak equivalences between cell complexes. So from this fact, it follows that actually, if X and Y are both fibrant and cofibrant, then this quotient of the set of maps from X to Y is actually the same as the set of morphisms in the homotopic category. And since we have an equivalence of categories which I wrote above, that means that actually we completely, we know how to compute Hom sets in the homotopic category for model category, because we just need to take a fibrant and fibrant replacement, and we will obtain the necessary objects which are equivalent to the initial ones. So this is one useful feature of model categories, is that we can explicitly compute localization just by merging out by some equivalence relation. Okay. Now I wanted to talk about another aspect that is related to this easier way of localizing model categories, namely the derived functors. So okay, so assume that we have a functor G from M to N, where M and N are model categories, or more generally, just categories with weak equivalences. Then what we want to do? Well, we have this functor G here, and we have two homotopic categories of M and N respectively. Then ideally we want something that descends to the homotopic categories. So some homotopical version of the functor G. Of course, G not necessarily preserves weak equivalences, which means that it not necessarily descends to a functor between homotopic categories. However, this can be somewhat remedied by considering the closest approximation to this descent to homotopic categories. And so this is where the notion of a derived functor comes from. It's just an approximation of a functor on the level of homotopic categories. So how we do this? So total left derived functor of G, denoted by this bold LG, is a pair which consists of a functor and a natural transformation. So the functor n goes from homotopy category of M to homotopy category of N. And the natural transformation C goes from the composition gamma prime G to the composition N gamma. So it looks something like this. Analogously, one defines the total right direct functor denoted by there's also a pair consisting of functor and natural transformation. So the functor goes in the same direction, and the natural transformation goes in the opposite direction. So we have transformation from N gamma to gamma prime G. The language of Khan extensions what we have is that the total left direct functor is the right Khan extension of the functor gamma prime G with respect to gamma, and conversely, the total right direct functor is the left Khan extension of the same pair of functors. Okay, so this passage did not require M and N to be actually model categories. We just needed some notion of weak equivalences, and then we can say that we have a homotopy category, which is just the localization. However, if M and N are model categories, then there is a specific kind of functors for which we can guarantee existence of total left and total right direct functors. And also we can describe these functors explicitly. Of course, there is a semi-explicit formula for Khan extensions, but it is not as explicit as what we're about to construct. So the upshot here is that in case of M and N being model categories, the total left and total right direct functors admit relatively simple description. So let me define for which functors we have such description. These kind of functors are called equivalent functors, equivalent junctions. So let M then be model categories. if F is a left adjoint which preserves cofibrations and trivial cofibrations, then F is called left Boolean function. If U is a right adjoint, which preserves vibrations and trivial vibrations, then U is called right Boolean function. Finally, if we have an adjunction between model categories, it is called Boolean adjunction if F is a left Boolean function. Okay. So now, of course, it is not hard to see that this condition can be dualized, and it is the same as requiring U to be the right Boolean function. So if one of the adjoints is a Boolean function, then the other one is also Boolean. Okay, so now we're ready to define total left and total right direct functions of a Boolean function. So once again, let M and N be two model categories. And assume that F from M to N is left Boolean function. And have the total left direct function between homotopy categories, which is defined as a composition of the following form. So here Q is a cofibrant replacement functor which takes an object and maps it to its cofibrant replacement, which fits into the diagram like this. since the factorization of the unique map from the initial object to X is factorial, Q is indeed a functor, and it induces a functor between homotopic categories. It requires some work to see that under the conditions on F, namely that F is equivalent functor, it in fact descends to a functor from homotopic categories of vibrant objects to homotopic category of N. This is something known as Ken-Brown's lemma, and maybe next time we will discuss it in detail. But for now, we'll just have to believe that this is the case. Okay, so dually, one defines total right derived functor denoted by R of F, R of U for right equivalent. And if we had a natural transformation of left equivalent functors, then we can define the total left derived natural transformation, which is obtained as a composition of a homotopization of the cofibrant replacement and the natural transformation restricted to the subcategory of vibrant objects, where it can be seen that it descends to a homotopic category. So yeah, and we have for the components of this total left derived natural transformation, we have the following identity. So and similarly for the natural transformation between right functors. Okay, so let me give you an example of a situation where equivalent adjunction appears in the context that we already discussed. So have the following proposition. So consider an adjunction between two abelian categories. For simplicity, one may think of categories of modules over subrings. So assume additionally that L preserves monomorphisms. Then we have equivalent adjunction on the category on the categories of chain components, which is induced just by applying these functors to each degree. So let me prove this proposition. So yeah, is equivalent junction. So since we have a pair of functors between abelian categories, they preserve split epimorphisms. So functor preserves split epimorphisms. Since R is a right adjoint, it implies that R is a left exact functor. And this in turn implies that it preserves kernels. So now we can use the characterization of injective objects in the category A that says that so the characterization of injective I's in A is such objects that the functor, well, the representable functor form to I maps monomorphisms to epimorphisms. And hence, it implies that R preserves injective objects. Since L preserves monomorphisms, it implies that well, it implies that by adjunction isomorphism, L preserves all cofibrations and R preserves all fibrations. So this is in accordance with the definition of model structure that we gave on chain complexes. I have some questions. Oh, okay. So the recordings will be posted both on researchseminars.org and also on the website, the seminar. Okay. So this implies that we indeed have a proven interaction. Okay, so as an example, one may consider the right equivalent functor, which comes from the functor of the following form for some fixed R module M. And then to compute its total right derived functor, one needs to just just take the value of this functor on the vibrant replacement of say complex C, where vibrant replacement in this model structure is precisely an injective resolution of C. So this was somewhat of an explanation how this usual stuff with direct functors in homological algebra fits in the context of model structures on chain complexes. So this was actually one of the motivations for the notion of model category. It was to treat homological algebra similarly as we treat topology. And well, this somewhat illustrates it. Okay, so now I think I would like to finish my talk with a short discussion of equivalent equivalences. So let me give you a definition. It is actually quite simple. So given equivalent junction, equivalent equivalence, if on a homotopic categories we obtain an enjoint equivalence of categories. There are, of course, equivalent formulations of this property more amenable to calculations, but we can define it just like this. And so I think that I will finish today with a list of useful equivalent equivalences that we will discuss in the future. So Equivalence theorem states that there is an equivalence between category of topological spaces with equivalent model structure, which was described above, and the category of simplicial sets, also with equivalent model structure, which we also described. So this equivalent equivalence is given by an adjoint pair where the left adjoint is a geometric equalization functor, and the right adjoint is the singular simplicial set functor of a topological space. So this is probably the most famous example of equivalent equivalence. However, there's also another very important example called Dold-Kahn correspondence. It states that for an arbitrary abelian category, we have an equivalence of simplicial objects in A and chain complexes in non-negative degrees. So this is also equivalent equivalence. So another example is the monoidal Dold-Kahn correspondence. It looks like this. So it works in for algebras for simplicial algebras over a field of characteristic 0, and it establishes equivalence of these simplicial algebras and commutative differential graded algebras connected commutative differential graded algebras over the same field. So here n, as before, is a more complex of simplicial object. And gamma tilde is not so straightforward to define, but it exists, which is important. So finally, one of modern applications of model categories is so-called categorical model structures. Which give equivalence. These are model structures on various models for infinity one categories, and all these model structures turn out to be equivalent to one another, thus establish an equivalence of models for infinity one categories. So I will just, this is not a complete list of such structures, but I will list just 3. So we have simplicial categories, simplicial sets with dual model structures or quasi-categories, and finally we have complete Siegel spaces. which is some kind of bisimplicial set with additional conditions which explain its categorical nature. So yeah, so this is another example of well, several Quillen equivalences, in fact, and I think that this is it for my introductory talk. I mean, I tried to explain various contexts where model categories appear and where they're useful and where we will study them. And now maybe I would like to just explain a bit how we think that this seminar should work. So basically, it's not like a course of lectures, but more of a reading group on various topics related to model category theory and spatial topology. So everyone is encouraged to give a talk, and well, if you have some specific topic in mind, you can present it, or you can just write me and we'll decide on a topic. And of course, on the website of the seminar, we have written materials for this term. Okay, I will stop the recording now.